Hello, this lecture will cover pages 1 through 6 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on capacitance and inductance, chapter 6a, capacitors and inductors. We're going to start out on page 1 of my lecture notes for the second half of the semester, chapter 6. We're going to talk about capacitors. A capacitor is a passive circuit element consisting of two conducting surfaces or plates separated by a non-conducting material called a dielectric. The capacitor is also referred to as a condenser. If you take a look in your textbook at page 220, I want to show you, these are typical capacitors right here. You're going to see these larger electrolytic capacitors which do have a polarity on them. And these other capacitors down here, made up of mica, glass, and ceramic, we'll be using a lot of the ceramic capacitors in the lab. But that's what a capacitor looks like in their smaller sizes. If you take a look here on page 1 of the lecture notes, I want you to notice that the capacitor is shown like this with its symbol. Sometimes you'll see it shown like this if it's an electrolytic capacitor, where this is the plus side and this is the negative side of the capacitor. But the capacitors we use in lab won't have a polarity assigned to them, but you do assign a passive current direction like we did a resistor. Capacitors are passive elements, so as current flows to the capacitor, it's a plus to minus. I might note right here that current does not flow through that capacitor. Current flows to the plates. Charges flow to the plates on one side and from the plates on another side. But you'll never get current passing through the dielectric. We'll talk more about that when we get to alternating current. The current, we said back in chapter number 1, was the rate change of charge with respect to time. If you take a look, comments regarding a capacitor. Energy is stored in an electric field. Energy is stored in an electric field on the in that capacitor. You're going to find out with a coil or with an inductor, energy is stored in a magnetic field, an electromagnetic field. But with the capacitor, energy is stored in an electric field. And the second comment regarding a capacitor is voltage cannot change instantaneously across its plates. These are both very important concepts. Now I'm going to give you a parallel for both of these with regard to the inductor, which we'll talk about later. Talking about a capacitor, energy is stored in an electric field as opposed to a magnetic field with an inductor. Voltage cannot change instantaneously across the plates of a capacitor, and current cannot change instantaneously through a coil. They're the parallels. But we're zeroing in on a capacitor now. The charge Q on its plates is proportional to the voltage across its plates. And the constant that makes them equal is capacitance. So the charge is proportional to the voltage. So if we start out with charge being proportional to the voltage, as charge goes up, the voltage goes up. As charge goes down, the voltage goes down. They're directly proportional. But the equation that relates them is charge is equal to the capacitance times the voltage. That's a very important equation you're going to need later. That charge is measured in coulombs. And the capacitance C is measured in farads. If you look at page number 2, just a little bit of mathematics here. Since the current is the rate of change of charge with respect to time, and charge is equal to C times V of C, there are two equations we just had on the previous page, then the current is simply equal to the rate of change of C V of C dt. I'm just making a substitution for Q on this first equation. That yields a very important equation you have to memorize as quickly as you can. We're going to use it much over the next 4 or 5 weeks. The current to a capacitor is equal to C dV of C dt. In other words, the current to the capacitor is equal to the capacitance times the rate of change of voltage across that capacitor with respect to time. Very important equation. We can use this equation up here, and we can isolate VC at T. Everybody can go from this equation, and I did it here, isolating the VC. The derivative of VC is equal to 1 over C ISC dt. Integrate both sides, you end up with the equation, the voltage across the capacitor, across the plates of the capacitor is equal to 1 over C, the integral from the beginning of time, when we're concerned in the circuit, we'll call it minus infinity, up to a particular time t, of the current with respect to time. So I'm just going to divide this equation up into two parts. I'm going to take it everything before t equals 0, and I'm going to call that an initial condition. Just take a look at this integral right here. I'm going to integrate this from the beginning of time up to t equals 0, and I'm going to call that initial condition, the voltage across the capacitor at time t equals 0. We're going to be talking about we're going to talk about this later, but most of the time the initial condition will be 0 volts at t equals 0. Not all the time. Plus, and this is the concerning factor as well, from t0, which may be time t equals 0, but we're just referring it to t0, where this left off, to t, 1 over c, the integral from t0 to t of the current with respect to time. Now, this is the voltage across the plates of the capacitor, and all I did was divided this integral up into from the beginning of time to t0, and I called that an initial condition, and then I go from t0 to some time we're interested in. So if you know this, if you've memorized this equation, it's easy for you with your mathematics skills to go down and end up with this equation. If you look on page number 3, the power delivered to that capacitor is equal to the voltage across the plates of the capacitor times the current to the capacitor. Making substitutions from the previous page, the power with respect to time in a capacitor is equal to C times the voltage times the derivative of the voltage with respect to time, and that's in watts. The energy stored, which if you take a look in your textbook, it's very easy to come up with the energy stored once you know the power. So we derive the energy stored from the power, and there's no integrals involved because we're taking the integrals up here to get the energy. The energy in joules, or the work, is equal to 1/2 the charge squared divided by the capacitance. You're going to use this equation in your homework and on the exam. So if you want to know the energy stored in a capacitor, there's no calculus involved here. It's simply equal to this equation. Practical capacitors have leakage resistance through the dielectric, which is in between the plates, that prevents them from holding indefinite charge. But we'll consider them ideal for now. But this is what a practical capacitor looks like. An ideal capacitor would look like this, which I showed you on the previous page. The practical capacitor has a leakage resistance which we parallel to the ideal capacitance. That's the resistance through the dielectric. No current flows through there other than a leakage current. You don't want it, but you get it. The leakage current is very high. Therefore, for the ideal capacitor, we're going to assume that the resistance that gives you that leakage current is infinity. So here's that leakage resistance. We're going to assume it's very, very high, so the leakage current through the plates of the capacitor is essentially 0. So we'll be working with this capacitor right here. The units of a practical capacitor range from a few picofarads to thousands of microfarads. Ideally in lab, we're going to be working with a few picofarads, maybe some nanofarads, up to maybe 5 microfarads. That's the range of the capacitance values we'll be using. And if you take a look here at examples 6.1, 6.2, 6.3, and 6.4 in your textbook, let's see, here they are. Here's problems, if just to recognize them. We know the charge is equal to capacitance times the voltage. If you isolate for capacitance, you can work out problem 6.1. Here's problem 6.2 in the book. Look it over. It's a simple derivative to get the answers here. And then you have problem 6.3 and 6.4 in the book. Just make sure you look these over and you can understand how to get those problems. Inductors. An inductor is also a passive circuit element consisting of conducting wire, usually in the form of a coil. So a conductor is sometimes referred to as a coil. If you take a look in the textbook, these are simple examples of coils. We've all seen coils before, but this is what they look like. Different pictures of coils there. Notice that we have a coil in a circuit here, and it's a passive sign convention, plus the minus, as current flows down through that inductor. That's the current to the inductor with respect to time. Here's the voltage across the inductor with respect to time. Inductance is measured in henries with a capital H. We have three passive elements now that we're going to be working with: the resistor, the capacitor, and the inductor. They're all passive, and you always have to put this sign convention in as current flows through it, just like we did in the first couple chapters. The voltage across the inductor with respect to time is equal to L di dt. Notice the difference between the current to a capacitor is C dV dt, and the voltage across an inductor is L di dt. This basically says that the voltage across the inductor is proportional to the rate of change of current. You have to think about that. The rate of change of current. The voltage across the inductor is proportional to the rate of change of current. The rate of change of current. L is a constant measured in henries. So what makes this an equation is that L, that inductance. Just like we did in capacitance, you could go ahead and isolate IL, and you end up with this integral down here, where we're telling you that the current through an inductor can be set up of an initial condition, the current at time t equals 0, or the current at time t0, plus 1 over L, the integral from that point t0, from that time t0 to some point in time, of the voltage with respect to time dt. If you have this equation, you should be able to get this equation. Comments regarding inductors. Energy is stored in a magnetic field, and current cannot change instantaneously through an inductor. Let's compare this to the capacitor. The capacitor says that energy is stored in an electric field. In an inductor, the energy is stored in a magnetic field, that flux that gets built up. In an inductor, current cannot change instantaneously through an inductor. For a capacitor, the voltage cannot change instantaneously across its plates. There are four concepts and four equations you should get down as quickly as possible. The power is always equal to the voltage times the current. This is on page 5. So from the power, we can get the energy stored. And here's the mathematics. I showed you the mathematics here. I made a substitution up here for the current, or for the voltage. The voltage was L di dt. I put it in down here, and I end up with the power is equal to L times the current times the derivative of the current. And from that power, I can determine the energy stored in that magnetic field in terms of joules. WL with respect to time, that's energy stored in joules, is 1/2 the inductance times the current squared. You're going to be using this equation. A couple problems. Practical inductors have resistance in coils and capacitance between the coils. So if you take a look, here we have these coil, and it has built-in resistance. There's your series resistance. And each one of these can be treated as a plate, and a dielectric as air, or some core in between. If you look at these, they're a bunch of plates. That's that inner coil winding capacitance. So an ideal inductor has this resistance, distributed resistance, and it has this inner coil capacitance at high frequencies. Okay, this can come into play. So you have to know that coils can be modeled like this, but at low frequencies. Okay, very, very low frequency. We're just going to treat it as a pure inductor. We're going to forget about this, and we're going to forget about that resistance. We're going to treat them ideal in class. If you take a look in the book, there's an example 5, and you'll have a couple problems like this to work for homework, where they want you to find the total energy stored in this circuit. They want you to find the total energy stored in that circuit. Well, what you need to do, if you look at those two equations I gave you on the previous couple lecture note pages there, you're going to have to find the current through these inductors. So we're going to assume DC, which means there's no rate of change. Think about this. There's no rate of change if we're going to assume DC, 9 volts here and 3 amps here. So this is going to look like a short. These inductors, these coils are going to look like shorts, just wires. You just need to find the current here, and you need to find the current here. Then you can go back and use this equation here. The energy stored in each one of them is 1/2 that inductance times the current squared for this one and for this one. And you just have to find the voltage at this point with respect to ground. In other words, find the voltage across C1 and find the voltage across C2, with these looking as open circuits. Remember, current can't flow through these capacitors. So in the steady state in this circuit, we call it the steady state. This circuit looks like this, where capacitors are just open circuits and inductors are just short circuits. So before you can work this problem and use this equation here, for the inductors you need to find the current. And what about for the capacitors? Here, for the capacitors, where was it? Here is Q squared divided by C. Remember this? Energy stored is 1/2 Q squared divided by C. Well, I gave you a previous equation that says Q is equal to C times V. So you should be able to determine the energy stored in each of these capacitors by knowing the voltage, okay, and knowing the capacitance. And that's all they did down here. The total energy stored was just the sum of all these, once you use those previous equations that I've given you. Make sure you can do that problem. And then there's an example problem 6.6 in the book. Look it over. It's a simple problem as well. If you have any integrals and any differentials here in these problems on the exam, they're going to be simple integrals and simple differentials. There'll be nothing difficult there. And that should conclude this lecture, and we're gonna continue on with working with inductors and capacitors through the next 3 lectures of this chapter, but that includes this lecture.